Okay, so last time I'll talk a little bit more about, well, just the barest amount about what we call solid state physics. And so I introduced the notion of binding between two atoms, where there's the separation between the atoms, and I said if you, I mean, is that hard to read? All this yellow in the background? I almost can't see it, and I'm standing right here. Let me try the blue chalk. And then if someone else is teaching after this, it's going to be completely hopeless. Oh, is that better? Yeah. All right, so if you bring in the two atoms, let's talk even like, let's just say there's the 2s orbital, and if I bring in two atoms, the 2s orbital would get split into two parts. And I argued about how, just in a very crude way, you're thinking of maybe two wave functions either added coherently, which kind of forms a wave function which is more or less one hump, versus if you add them with a sign change, and you get something that has two humps, and two humps has higher kinetic energy, and it's a higher energy state. And they're spatially different states. The one state is kind of the electrons in the center, and the other is the electrons more separated. And so even though the electrical energy is minimized with the electrons separated, overall the kinetic energy wins out. And then I said right at the end that that's a sort of a generic idea that this will apply to all the states. So if that's 2s, then the next state would be 2p, and it will split. Now, the interesting thing is that if I bring in more atoms, and I can show this analytically, if you bring in more atoms, if you bring in 3 atoms, any one state splits into 3, okay, as I bring the atoms together. If I bring in n atoms, where n is big, like Avogadro's number, this is what happens. I'll have n states in there. All right, and if n is like Avogadro's number, then for all practical purposes, that's just a continuous set of states. Sort of almost like a classical thing, where there's just no real restriction. Yes? Yep. Where there's no real restriction on the energies. And just this very simple picture actually explains a lot of behavior of solids. So first off, do you form a solid? So what do I mean by that? So if I have a bunch of atoms of a certain size, if I have a bunch of argon atoms, argon's a noble gas, you put them all together, do they form, argon metal? The answer is no. If you have a bunch of nitrogen atoms, you put them together, what happens? Well, you get N2 as a gas, but then that doesn't form anything. So when do things form as a solid and when do they not? Well, it depends on the nature of how these energies split as the thing came, as the distance between atoms was brought together. And actually calculating that is, subject for an entire senior year class. But there's kind of one just simple idea you can see from it. If this was the energy of a state when all the atoms were separate, and you again, versus separation, you bringing them in, if the overall curvature is something like this, and by the way, once you bring the atoms very close together, I didn't draw it over there, but it ought to shoot up. Because if you bring the atoms really, really close together, then the Coulomb energies are going to get really, really intense. And the energy of that combined state is going to be really high because of Coulomb repulsion. But if it looks like this, where basically the average in here is a little bit lower than when they're separated, then that's binding. Okay, and then wherever this is at a minimum, that's going to be some separation between the atoms. And this is typically going to be on the scale of A0. Or maybe a few A's, a couple A0. A0 being 0.529 angstroms, half an angstrom, right? And so then that'll be the spacing in a material, okay, like a crystal or a metal, okay? And so it's just the notion that, I mean, when I drew this, there was a state that was kind of the binding state, and then there was the anti-binding state. But in fact, I fill them all in. It could be that overall this band is a little bit lowered, or for some materials it's a little bit raised. If it's a little bit raised, it won't form a solid. Because remember, when you look at an energy picture, there's this notion that if I have a particle out here, or I have a collection of particles here with this energy, if I come over here, if this is deeper, less energy, that's bound, right? I can think of this as sort of like a potential, and forces are always pointing at the derivative of the potential with a negative sign. And so the average here is looking like that. So I'm going to roll downhill to, a point where the potential is minimum, right? That's just the basic notion of binding when looked at it in an energy diagram. Okay, so the point I want to make is these original orbitals, literally the orbitals of the atoms, form these bands, they're called. And so then the bands determine a lot of materials. The bands are all important. In particular, let's think about metals. Since I went and calculated, based on from statistical mechanics, I calculated, and I think you should be, this is something you need to be responsible for. I put it in the homework sort of, calculating that density of states for the free electron gas, because that's what the electrons in a metal are like. So in this picture, what's a metal? Well, the simplest metal you can think of is the third element, lithium. So actually, it's almost on this diagram. What I'll do is I'll take this picture where this is the 2s orbital, and there's the 2p orbital. There's also a 1s orbital, okay? And let me just redraw it. For just the sake of having nothing better to do, people draw a horizontal axis here, but they don't really mean anything by it. Maybe this is some direction in the detector, in the crystal. I'm not talking about the separation anymore. I'm just allowing myself to draw a band, and in this band, I mean, this one would say come from the 2s orbital, and then there's the 2p orbital. We'll have another band. There's also another notion I should kick in. If I have an atom, like the innermost electrons in the 1s orbital, they will never overlap typically. Their wave functions will never add between the two of them. They're tighter, they're smaller, and I haven't really brought them close together. And so this picture is only going to apply for the couple outermost orbitals in the atom. The inner ones are just going to be bound doing their thing. Realize that for a heavy atom, like say lead, the inner shell electrons are bound by 80 keV. You can easily derive that from the Bohr formula, 13.6 electron volts times Z squared over N squared. If N equals 1 and Z is 82 for lead, it's about 80 keV, okay? And so those electrons are just totally not participating in the binding when the atoms, if you form a brick of lead. It's only the outer shell electrons which are doing this. But just to take the lithium example, so lithium is Z equals 3. That meant there were 2 electrons in the 1s orbital. 1s2 would be the atomic notation. They're there. They're sort of out of the picture. The 2s orbitals from multiple atoms overlap, and they form this band. And after you take the first 2 electrons and put them in the 1s state, there's 1 electron left over. Each band, I wrote n. It's not n states. It's 2 n states because of spin. Okay? There's n states, if you will, spatial states. But each can take spin up, spin down. Okay? So there's 1 electron left over, and this band can take two electrons per atom, and so it's half full. Okay? And this is my electron gas. This is my quantum gas for which we computed the density of states. And then, for instance, we found the energy at the top of the band as a function of n over v. We wrote down the formula. All right. So what makes a metal? It's a simple idea, a little bit subtle, but straightforward in a way. It's when you have these bands and you fill one up halfway. Now, what do we know about a metal? A metal is something that conducts electricity versus an insulator. An insulator would be the next atom, boron, which is Z equals 4. In the same picture, this would be 2p, this would be 2s, this is energy. Since there's 4 electrons, they completely fill this band, and they leave that band empty. This distance between the bands is called the gap, E gap. Use an epsilon just by convention. Now, this is an insulator, and that's a metal. And so why? The reason is, it has to do with this notion of, well, it comes back to the fact that electrons are fermions, and how many electrons can you put in a state? If I have a band, let's do the insulator first. It's a little bit easier to understand. If I have this band, I have electrons filling up every single possible state. They're in there. Now, one notion I should mention is that when you have this band, what is really fascinating is that does mean each electron totally is decoupled from the atom it came from. There's no real meaning, again, in this sort of notion of, well, these weird things about quantum mechanics where you can't distinguish particles. In a very similar way, if I have an electron in a band, it's basically throughout the material, okay? It'll have a very long wavelength, and it's just sort of wandering around. And they're all doing that, so they're all in these states. If I put an electric field on it, if it's a metal, you would think electrons move in response to the electric field. Well, for an electron to be sitting there, and then it feels an electric field, and then it starts to move, it has to gain a little kinetic energy. Just gain a little kinetic energy, all right? To gain a little kinetic energy, it has to go to another state, right? If it's at some energy, it's filling up all these states, and this was their energy. If I want to gain a little kinetic energy and move in response to the field, I have to go to another state. The problem is, all the states are filled here. And there's not a single empty state. And so there's not a single electron in this entire band that can do anything in response to anything. They just can't. They actually are moving, but there's going to be as many moving left, as moving right, as moving up, as moving down, as moving that way, as moving that way, okay, in all directions. And it's just a totally inert thing, and that's an insulator. No electrons can move in response to an electric field. Whereas if I look at this band, if I plot how many electrons fill each energy, this is the Fermi energy, I get that same Fermi-Dirac distribution I talked about, where this is the Fermi energy. And I'll have this all filled in, 1 electron each, well, 2 when I include spin, in all these lower energy states. So this energy here is basically the energy there. You could think of this diagram, if I try to project it here, this diagram, I'm mapping down over to here, all right? And I fill up to a spot, and basically an electron there these are empty, these are states that could have an electron and don't. And this electron can jump over to here. Or put this way, these are empty states. An electron can be promoted up. So if there's an electric field, electrons near what's called the Fermi edge, near the energy that's the top energy, get promoted up by the electric field. They get a little electrokinetic energy and they move. And so a filled band versus a half-filled band makes all the difference in the world. And so in fact, you can go through the periodic table and you can more or less say, oh, those are going to be metals and those are going to be insulators simply by looking at the columns and deciding if you've come to this point where you've just haven't filled the band or have filled the band. Okay? And it, and it has a huge, profound difference for how the materials behave. Any questions? And it's really that simple a concept. I'm not doing any math here, other than thinking through what it means quantum mechanically to be locked into a restricted set of states. I think it's kind of a subtle consequence that because you're in these, because you have no state you can change between, because all states are full, the electrons are inert in the material. There is the idea that if I'm in an insulator, where's my blue chalk? If I'm in an insulator here, why can't an electron get promoted in energy up to here? Well, it can, but typically this may be on the order of a few electron volts. All these energies are a few electron volts. Sometimes as many as 10, more often about 4 or 5. And as I explained before, in terms of Fermi energies, that's equivalent to a few tens of thousands of Kelvin. Okay? So it just isn't going to happen thermally, and for a small electric field, it's simply not going to happen. Now, you've heard of semiconductors. What's a semiconductor? And you know that it's important. You know that you wouldn't have a watch, you wouldn't have a computer, you wouldn't have an iPhone, all these good things if there weren't for semiconductors. A semiconductor is a material where this gap is small. Okay? If E gap is, it's actually a very loose definition, but something like that, then you call this a semiconductor. Because for a semiconductor, Avogadro's number being what it is, even though there's this picture, and it only, we're not talking about a metal with a half-filled band. We're talking about a material with a fully filled band. Some electrons will get thermally promoted across the gap. The gap's small enough that KT does, there's a probability, which is like E to the minus E gap over KT. And so even though E gap is 2 EV and KT is equivalent to 0.03 EV, this is E to the minus 2 over 0.03, E to the minus 60. It's not 0. It's small, but it isn't 0. In fact, I don't think I did that number right. But it's not 0, 0, 0, because basically there's a prefactor, which is Avogadro's number. And there are some electrons which are promoted. Well, that actually, okay, so I finished telling you about a metal and an insulator. Just a couple words about a semiconductor, because they're so important, and it's really an incredibly rich subject, and I'm only going to say a couple words. That's not really the interesting thing about a semiconductor, that some electrons are promoted across the gap. What's interesting about a semiconductor is it turns out that's not really the story that's important. The story that well, actually, I forgot one thing before I tell you the story that's important. This gap here, there are no states there. It's called the forbidden gap, okay? Because I started with atomic orbitals. This represented an original atomic orbital. That did too. There just was no solution to Schrodinger's equation in here and up there, okay? So now, oh, and also just a little bit of language. This is called the conduction band. And this is called the valence band. Okay. Now, let me just erase this E gap. It is still E gap. I'm just going to erase it. In a semiconductor, one of the things that's interesting is that your material is actually never quite pure. And actually, in the case of silicon, we deliberately don't keep it pure. We dope it, putting a little bit of an impurity. And there's two types of impurities you can put in, which basically introduce electrons at this level or that level. And electrons here, they're called acceptors. Basically, electrons sit up on them and leave behind the absence of an electron, which is called a hole. So I have this fully filled band of electrons. I add this impurity. The impurity will absorb will take up electrons in a slightly higher energy state. It's close enough that KT will thermally excite some electrons to sit on those impurity atoms and leave behind missing electrons from the filled band. We call them holes. And it's kind of a nice concept. All it is really that you had available states and there were electrons missing. But you can think of it as a particle with positive charge. And if you put an electric field on, these holes will move around in response to it. You can also do the opposite and put impurities here which will kick an electron up into a state. So these are called donors because they'll donate. Those are donors. These are acceptors. And so you could produce electrons up here. And I only wanted to mention this because you may well have heard of there's p-type silicon and n-type silicon. You may have heard that there's a thing called a p-n junction. And certainly you've heard of a transistor. And a transistor is basically a structure where I have p-n-p or n-p-n, a combination of the two types of materials put together 3 times. What are those materials? If I put in the thing that gives you holes, which basically gives you positive charges which can move around, that's called p-type for positive material. If I put in, I don't put in both. If I put in instead the thing that donates electrons, I produce a set of negative charges which can move around in the material. That's called n-type. And what's interesting about it, and it's really subtle to go through in detail, and I'm not going to, but the key point is simply this, that if I have like a metal or an insulator, it's a metal or it's an insulator, and there's really nothing I can do with it. If I have something that's kind of mildly resistive, I can make a resistor, okay? And then I can study Ohm's law, you know, V equals IR. I can prove it, I can measure I, and I can measure V, I can measure R, and that's about all I can do. And it's, frankly, there's nothing interesting you're going to do with that. Well, you can transmit power. That's interesting. You can light a light bulb. So, okay, I denigrate Ohm's law. We had lighting, and we've had electrical motors when we just have, you know, sort of resistive materials, and that's about it. But once people figured out that you could make materials where you could basically make a material that has positive charges which are free to move around, or negative charges which are free to move around, if you put the two of them together, you start to get really interesting devices. If you put a P material next to N material, it forms what's called a diode. And that means if you put an electric field such that you're trying to push electrons with the electric field, that would mean an electric field that way. It's going to push electrons that way. If this is the N material, which has extra electrons, then it'll say, okay, fine, they go. But if you swap it around, where this only has extra holes, and you try to push electrons that way, there's charge that can move around here, but it's holes, not electrons. And you could push all you want with an electric field, and no current will flow. So that's called a diode. It's a thing that only flows a current in one direction. Now that's mildly more interesting than a resistor. Then it turns out if you put p-type material and stick a clump of n-type material on it, you can make a transistor. And I am not going to go into any detail about how a transistor works, but I will say there is one important point about a transistor. What a transistor does is that in a transistor, the key idea is that if you change the voltage between two of the, you make a connection to, say if it's this p-type material with an n-type piece of material stuck on it. I mean literally, that is how they do it. The first transistor was a chunk of gallium, and they stuck this other thing, they smashed it onto it, okay? And you put wires on the 3 things. It's called a 3-terminal device. So you have a wire connection to each piece of the P part, and you have a wire connection to the N thing in the middle. And by changing the voltage between 2 of them, you change the resistance between the other 2. That is a big deal. That's a big deal because that means I can build a circuit where if I have one voltage, it'll change the electrical properties for another voltage. And I can make amplifiers, or I can make logic switches based on that. Basically, I could take a voltage on and off between this P and N, and I change whether the P to P is conducting or not conducting. And that's the basic logic gate. You know, yes, no. And so I can assert a yes or a no with one set of wires, and I can read the yes or a no with another set of wires. I'm saying this in a very simple kind of cartoonish way, but that basically is the key idea. If all you had is something that's kind of got some resistance, you can't do anything interesting with it in a way. And so that introduced the whole, you know, Semiconductors turns into circuitry that you can make like amplifiers, and of course more importantly, or at least equally importantly, more importantly, memory chips, processor chips, and all of the computer industry. So I'm going to stop there, and that's solid state physics is a huge field, or condensed matter physics. Semiconductors are only one tiny little part, although an incredibly important part. And the ideas build in the way I've shown out of like basic atomic physics, which comes from the Schrodinger's equation, which you solved. Okay. So any questions there? No? All right. Okay, let me erase the blue. Oh, and I'm sorry, a bit of business. Someone asked, I'm trying to get all the solutions. I've got like a backlog of solutions to post, and I am trying to get them up soon. Yikes. Okay, so let's shift gears. And this is following the book somewhat. To particle physics and nuclear physics. Okay. If I want to sort of tell like the history of nuclear physics, partly in a nutshell, people came to realize that atoms had electrons in the outside and some sort of positively charged nucleus on the inside. And so it was obvious, you have a nucleus with some charge Z, which is positive, and then you'd have all these electrons, which had a negative charge. And so they're stuck to the nucleus, and that's fine because there's electrical potential. But why would the positive charges want to be in the center? Because they have a force of repulsion between them. So that was the first mystery. Then the second mystery was people started to build simple accelerators, cyclotrons, and they started to smash atoms into each other, proton on proton, proton on heavier things, and they produce neutrons. They'd also seen them in cosmic rays, which are particles. Do I have chocolate over my face? Everyone is laughing. I knew there was a reason. Particles from, you'll just have to put up with it. So particles from outer space coming down create reactions on Earth. And people were able to see that there was a neutrally charged particle that otherwise acted much like a proton, but it didn't have an electrical charge. So that's the neutron. So, we know that the nucleus is neutrons and protons. So, I give up. So, as you probably know, there has to be some other force which does two things. One, it has to overcome the force of repulsion between all the positively charged protons. And secondly, it holds neutrons and protons together. And one thing that was kind of obvious is if you're going to overcome the force of repulsion in the nucleus is quite small. Okay? So whatever force that binds electrons and protons together, we know it's about an electron volt at the scale of an atom. Okay, the scale of an atom is an angstrom. Okay, a nucleus, that's 10 to the minus 10 meters. 5 10 to the minus 10 meters is half of 10 to the minus 10 meters is the scale of a hydrogen atom. And it's 13 electron volts. The nucleus we now know is 10 to the minus 15 meters, a Fermi. If there's two protons within a Fermi of each other, then that's 5 orders of magnitude closer than for the electron and the proton, right? And the energy in the Coulomb force goes like 1 over r, so it's 5 orders of magnitude higher. So there's got to be some very strong force holding the protons together. So we knew there was E and M, and now we know there's a strong force. Okay? We also have known that there's gravity. And it turns out there's another force called the weak force. You know what I wanted to do? I'm going to order them in terms of the strength. So the first thing to say is, what is the relative strength? The strong force is a relative strength of 1. The weak force is about 100 times weak. The E and M is about 100 times weaker. Weak force is about 1,000,000 times weaker. And gravity, for the same separation of particles, is 39 orders of magnitude weaker. Now, gravity we're all familiar with. And the reason why, how can gravity be weaker than electricity and magnetism, or weaker than the strong force, since you've never seen the strong force in your life? And even electricity and magnetism, if you haven't been shocked, you don't really deal with. And the reason is simply that these forces are so strong, you never see them in a naked sense. The MKS unit of a charge is a coulomb. You have never dealt with a coulomb. And anyone who has probably didn't live to tell about it, right? If you had a coulomb in your pocket, you're going to blow yourself apart, okay? So electricity and magnetism is such that positive and negative charges are always completely tightly bound up with one another. And chemistry, which all is about changes in electric forces, involves very, very small rearrangements of the energy levels. That's only a fraction of the total energy, and that's like burning and the food you eat and photosynthesis, right? It's just very small changes in that energy scale. Actually, we do know all about the strong forces. What powers the sun? And the sun is 93 million miles away, and it still warms us up. Okay, so the strong force is actually darn strong when it actually is naked, if you will, and exposed, but it's usually contained in a nucleus. Gravity just appears so strong because it is naked. It's not like there's a mass and an antimass and they're stuck together and the force is kind of contained in a little mass-antimass gravitational dipole. Okay? We don't have antimass that we can shield the Earth from, like a shell of antimass, and then outside there's no gravity. That's the analogy with an atom. When I have an atom, I have a proton, I have an electron, they cancel each other from the outside world, they don't see anything. So unlike all the sci-fi, we don't know about anti-gravity. We don't have an antimass where you could put a shell of antimass outside the Earth and then cancel the gravitational field of the Earth. Kind of interesting if there were such a thing, but we don't know of such a thing. So the reason gravity is so familiar is because all these objects like the Earth are really big. And there's a lot of particles, and so the gravity adds up, and so you see it. But this is the scale if I put particles right next to each other and I just measure the force between them in the different fields. Okay? There's another concept, which is the range of the force. E and M is 1 over r squared, and gravity is 1 over r squared, which is to say, in principle, it extends off to infinity with the force that falls off like 1 over r squared. And where does 1 over r squared come from? Basic geometry. It's simply to say that the force per unit area is the same. Not per unit area. The force over a whole area is, the flux out the flux of force from a particle is uniform into a sphere. So the further and further away you are, the size of the sphere is 4 pi r squared. So the amount of force at a given point falls off like 1 over 4 pi r squared. Very simple. Okay? It's you know, Newton's Principia, he did the whole darn thing with geometric drawings. He didn't write down, he invented calculus, and he did calculus as part of it, but he did it all with geometry, okay? And the 1 over r squared is just a result of geometry. If we lived in a 4-dimensional world, it would be 1 over r cubed, okay? But unlike that, the strong force is kind of funny. It's got a range of a Fermi that's 10 to the minus 15 meters. And so basically, if two particles are 10 Fermi apart, no force. No force, none, nada, zilch. And then if they get within a Fermi of each other, they feel the force. And then what's actually really bizarre is once they're within a Fermi of each other, they actually feel the force in a funny way. They actually ignore each other, except that they try to separate. So I know we could make analogies with relationships or something, but right, it's like, you know, absent makes the heart grow fonder, but if they get close enough, they kind of, you know, there is no force in there. So actually, a nucleus is a very funny thing, where the potential for a nucleus looks like this, versus distance. We draw it as a two-dimensional, you know, first off, it's very, very steep walls. I have to put a slope in there. The force, of course, this is the energy, this is the potential. Force is the gradient of potential always, okay? And so, zero slope, zero force, deep, really, really steep slope, very steep force pointing inwards, because that's a positive slope with a negative sign, so the force points inwards. Similarly, points inwards. And then at the bottom, it's totally flat again. So once the particles are inside, they don't feel a force. And that's just a reality. And in fact, we do understand this through something called quantum chromodynamics, the Nobel Prize for which was awarded in about 4 years ago. It's one of the triumphs of modern particle physics to explain why you have this funny force that, you know, sort of is really extreme if you try to get away from it. If I'm a particle, if I'm trapped in, if I'm a nucleus of a nucleon, I'm a proton, and I'm independent-minded, and I want out of my nucleus. The rules are, I can run around all day, and I don't feel the strong force, but if I try to get out, I feel this incredibly strong force keeping me in. If I get out, you know, waha, I'm completely free. And it just, you know, just as soon as I get out. So it has a range, and the range is a Fermi, and that's it. The range of the weak force is a fraction of a Fermi. And why is this? I mean, at the time in the 30s, or the 40s certainly, basically this picture was clear. Yeah? 10 to the minus 15 meters. You can, we call it the Fermi because Fermi was this fantastic turn of the century physicist. Fled Italy, came to the US, had a lot to do with the Manhattan Project, created the first controlled nuclear reaction under the bleachers of the football field at the University of Chicago, like 1941 or something like that. Sort of a Renaissance man. One of the few people that made big contributions in both experimental physics and theoretical physics. He's more or less a theoretical physicist, but actually led experiments. And so he has a whole bunch of things named after him. But if you don't like Fermi, it's a femtometer, right? So just after, you know, pico is 10 to the minus 12. You might know nano is 10 to the minus 9. Micro is 10 to the minus 6. Pico 10 to the nano 10 to the minus 9. Pico 10 to the minus 12. Femto 10 to the minus 15 in general. Okay? And it's the scale of a nucleus. What's interesting is that I'm going to write these words, see if anyone knows what they mean. Is there a massive force carrier? Anyone know what that means? Sounds cool. Yeah, what?
It's whether the force is carried by a mass particle with mass and a particle without.
Yeah, yeah. So, what is a force? Well, that's a deep question, okay? And there's many kind of layers of peeling the onion and talking about it. But we do know that one version of reality is that forces are carried by particles. The electrical force is actually carried by photons, okay? And what I mean by that is if you have a proton and an electron, and it's an atom, and the electron is just bound to the proton, it's a hydrogen atom. The way we think of it is that they're shooting photons back and forth at each other all the time. And they're called virtual photons because, and I've kind of mentioned this before, in some sense, using delta E, delta T greater than or equal to h bar over 2, for some short time, energy gets borrowed out of nothing to create a photon, which gets swapped back and forth, and then it's gone. And as long as it's gone before the delta T associated with that delta E, everyone's happy, okay? And that builds up the force. And the 1 over r squared law just comes from if these things are going to shoot photons at each other, the further out they are, you know, the bigger an area over which, you know, the photons from the proton getting sent out have to cover, all right? And so the photon is the force-carrying particle or the mediator of the electromagnetic force, okay? The graviton is the force-carrying particle of the gravitational force. Both the photon and the graviton have no mass, okay? So if I emit a photon from a proton, it just can go, and it gets diluted by geometry, 1 over r squared, but that's it. These other forces, so the answer is no, no. But the answer is yes and yes. Let's talk about the weak force first. In fact, sometimes people will say, no, there's not 4 forces, there's 3 forces. There's the electroweak force, and there's the strong force, and there's gravity. It turns out that the weak force and the strong force are kissing cousins of each other. In fact, effectively, the mediator, the carriers of the weak force and the carrier of electricity and magnetism, this photon, are the same particle just about, except that for the weak force, that particle has a big, big mass. It weighs about 50 GeV, c squared. And a GeV, remember, is the proton mass. There's two actual carriers of this force. One's called the W and one's called the Z. They're particles which we have measured. If you create them in an accelerator, which was done the first time in the 1980s in CERN, it was done in the first time where you could see it, measure it, and prove it. They're created all the time in, you know, cosmic rays. They only last for a very short time, and they decay into other particles. But they really actually are the same as, the only difference between these two forces is this thing has this really, really heavy particle. So when you try to create it in this sort of way, it has a really short leash. It can only go a really short distance before its time is up, and it essentially has to, you know, you got to pay the piper, and it, you know, it has to return to nothing. And so the force can only be carried over a very short distance, okay? I'm talking very vaguely, but I mean, I'm trying to simplify the result of very complex mathematics, but I'm not. I mean, this is reality. This is the way to look at it. The strong force is carried by what's called gluons, which are, well, they glue the neutron and proton together. Okay. And we say that the strong force. We like to say that there's a language we use, which is to say that particles that have the weak force are weakly charged. All particles are gravitationally charged. Some particles are electrically charged. A neutron is not electrically charged. And some particles have strong charge. Okay? And we don't really know what that means in a way. It's just a label you put on the thing if it has the force. I shouldn't say we don't know what it means, but realize that the notion that something is electrically charged, everyone's all happy with that, okay? Well, really all that meant is that particle has an electrical force. And so to say that something does or does not have the weak force and the strong force is very analogous. Yeah?
Does the mass force carrier correspond to like fermions and bosons? It's photons and gravitons and bosons.
The photons spin 1. The W and the Z, I'm glad there's no other physicists, senior physicists in the room because I forgot. They are spin, I think they're spin 1 also. Gravitons spin 2. Gluons are spin, I think they're spin 1. Might be the spin half. Does that answer your question? Yeah. I was prepared next to talk about the nuclear force. I'm running short of time. Let me skip the nuclear force for the moment. What are the particles we know about? Let me just list the particles we know about. That seems like better use the last couple of minutes. We know that there are quarks that make up a nucleus. And there's an up quark. Oops, we put that above. Up quark and a down quark. I've mentioned before, a proton, I believe, is an up, up, and a down. Neutron is an up, a down, and down. These guys have fractional charge of 1/3 or 2/3. The electric charge is 1/3 or 2/3. Then it was seen that there was a strange quark. And then it turned out there was another quark, and they called it charm, because they really liked the experiments they did that saw it. Then they got really pretentious, and they said, well, there's going to be another one called beauty and truth. Then they thought, oh, they got carried away, so they called this bottom and top. I'm not joking. That's exactly what happened. When I entered undergraduate, they called them truth and beauty, and then it just got too much for people. And then there's the electron, which you guys know about, and the neutrino, which you know about because I've told you about. Maybe you knew about. And then I told you about muons, which are created in cosmic rays. Okay? And it turns out associated with a muon is a mu neutrino. And then it turns out there's a thing called a tau and a tau neutrino. Then there's, okay, so these are the basic particles. Then there's the particles which carry forces. There's the photon, which is the electromagnetic force carrier. There's gluons, which carry the strong force. And then there's the W and the Z. That's a charged particle. That's an uncharged particle. These carry the weak force. And then there's gravitons. I think those are, well, and this is gravity. These are the particles we know about. These things make up most, neutrons, protons. Neutrons and protons are 3 of these things. It turns out you can make the analogy of a proton, up, up, down. You could do a charm, charm, strange. There is such a beast. And it will last a short time and decay. And there's this wonderful success of particle physics, which is there's these mathematical relationships between these things as to which you think might make particles, and then they do. If there's 2 of them together, it's called the meson. The simplest version of which is a pion. If you smash 2 protons at each other, you're going to produce pions, and you eventually might produce muons. But there's something special about the way I've drawn this. These are called the families. These are the families, this is sort of normal matter. All of these are stable. This next family up, this is basically increasing mass. These are called the leptons. And these particles make up the baryons. Or a better word is hadrons. I think baryon meant the ones that actually have 3. Like hadrons is the more general term. Or maybe yeah, I think that's right. And all these things can be created for short amounts of time in an accelerator. You won't typically create them by themselves. A quark, for complicated reasons, can never be alone. Okay? So they've never created a quark. These are called the quarks. And after they were postulated, there was a long period where mathematically they really seemed to be there, but people didn't believe the quark model because no one ever could see a charge of 1/3 or 2/3. And indeed, we never have. We now know that this is reality. These are what make up neutrons and protons. These leptons are, well, they're the other thing. And if for all of these, what is this, 12 particles, there's the antiparticles. Each one comes with its antiparticles. Okay? So I'll leave you with that. I'll leave it there. We'll talk about this more before Thanksgiving, for those of you who can make it.